and that's asphalt concrete, HMA. It's very simple, and we are going to learn basically putting everything together, what you know about asphalt binder and aggregates, to see how this all translates into designing HMA pavements. The sections of the textbook is actually exceptionally good for pavements because the authors are actually researchers in pavement materials. So if you want more information, the sections of the textbook that you can look at are these. So we talked about having what asphalt concrete is before, which is asphalt binder and aggregates. And you saw that you also have some air voids. And I told you that we have about 4 million miles in the US. 2.5 are, around 3 actually now I think, are paved, and 95% of those are asphalt pavement. So it's very important material. And we will talk about the production also a little bit. It's typically in drum plants, and we also have learned the failure mechanisms. Those are essential in designing the pavement because we want to prevent them from happening. And those failure mechanisms are the 3: thermal cracking, fatigue cracking, and rotting. Exactly. We already learned that. So the only method that we learned today to design is the super pave method. There are other methods you'll see in the book, but what we use is super pave, and these are the steps in super pave design. So material selection, then aggregate selection, and then binder content calculation. So this is a little bit of calculation that we need to learn today. And at the end, you also have to check for moisture sensitivity. Because remember, if you have water in concrete, it's going to strip the asphalt off the aggregates. So you're going to have a big problem. So our goal is basically to design a pavement with these properties. So it has to be resistant to permanent deformation, like rotting. You have to have enough resistance to fatigue because repeated loading is unavoidable. All you have is truck loading. It is repeated loading. And then thermal cracking, aging, which we also have talked about what it is. Moisture damage, which I'll tell you a little bit more today. And then some other properties, which may not, these are not structural, like a skid resistance. You need to have material with enough friction on the surface. Otherwise, if it rains, what happens? There will be a lot of accidents, right? So the texture has to be also conforming to some standards. And then you want to have material which is workable. The binder should be such that you can actually place and pump the material. And of course, cost. You need to make sure that whatever you are doing it economical. We are not going to go to the details of all of that, but this should give you an overview of what the purpose of the design is. Like a skid resistance and texturing, it's its own topic. We're not really going to go to the details. Questions about this? So now, just before going to the process, let's remember the structure of asphalt aggregates, and then you have absorbed binder, which are in the pores, and then you have the effective binder, which is actually the glue which holds everything together. If you have too much of that, the material deforms too easily. If you have too little, you don't have enough glue, it's not stable enough. And Now, if you have water and the aggregates are such that they want to absorb water, they are hydrophilic, then they are going to absorb water. And you even know that if you want to glue two surfaces, if one is wet, what happens? The glue peels off. You cannot really do that. You have to dry and clean, right? Exactly like here. If the aggregates are hydrophilic, then, and if you have moisture going inside the material, the glue is not going to do its job. So the binder is going to be stripped off the aggregates, and you are going to have what is called a stripping or moisture damage. So this is something that we test the material for at the end. It's going to lead to the loss of tensile strength and premature failure of the pavement. So if you hear ever stripping, this is what it means. And you can see here in the picture, I forgot to show you that, you see there the binder has been kind of stripped off. So you can see the aggregates compared to the picture to the left where everything looks much darker. Okay. Another thing that we need to know about is this concept of easels. Easel is equivalent single axle load. So to be able to translate the traffic load into a quantity that we know how to, a quantity which is a standard between different communities, people have defined the equivalent single axle load. So if you have mixed traffic, for example, you have different types, you expect to have different types of trucks, buses, etc., you can convert them all into one number at the end. So a truck will be converted to a number of easels, and then if you have smaller trucks, would be a smaller, etc. When you collect traffic data, then you translate that into equivalent single axle loads. And we don't really care about cars. Like, their effect is so small compared to the trucks that we just ignore. If you want to compare, like a truck, a passenger car is 0.0006 easel. That's nothing. In comparison, a semi truck is 3 easels. So you can see that why we don't care about cars. So don't feel any sort of guilt when you're driving on a pavement. You are not really doing much. Unless you have a truck, I mean. This I don't know. Like real big truck, 18-wheeler or something like that. Another thing that we didn't talk about before is the speed of traffic. What do you think? Of course, more traffic, higher volume means more easels. What do you think is worse for pavement? Slow or fast traffic? Yes, exactly. And you will see that this is something you need to account for. So this causes more load, and we need to account for it. So remember that cars are innocent. It's more like trucks and buses. Okay, now we are ready to go through the SuperPave steps. So there are 4 steps, as you can see. We start with material selection, and the good news is we already know how to do it. You already have learned to design binder, right? We need to just learn a little bit more details. So the binder, we have to choose it, you learn that, to avoid fatigue, thermal cracking, and rotting. Aggregates, you want to have them to provide a stability and a strength. So they have to be angular, and they have to be to have a continuous gradation, as you will see. That means that you want to have all different sizes in your mix. So what we need to do is to review that a little bit. I already shown you, and you have done the homework on binder selection, and we already learned how to do that, right? For 50% reliability, you look at the average values, and then you go to a table, and you pick what is available, being conservative. You all know that, right? So here, for example, we have 56 and negative 23. We don't have these numbers in the table, so we go with PG, which is performance graded, 58, 28. And what do we do for 98% reliability? Right, try to do that very quickly on your own, so you are engaged and you don't feel bored. Very quickly, it should take you like 30 seconds, really. You did it in your homework. You have 56 and the standard deviation is given 2 and 4. If you are curious, 100% of this class completed SRT. 100%. So really good job. Whatever you did, it worked very well. I've never seen this before in my life, so probably will never see it again. You are either very good friends or I don't know. Whatever you did was very effective. Okay. So we have to add 2 times the standard deviation and subtract. So you get these 2 numbers, you go to the table, and you are going to come up with another binder. Make sure your numbers are correct. So you have these. So something that we didn't talk about are some corrections. So if you have very high traffic volume, because you expect a lot of deformation, that behaves like having higher temperature. Does it make sense? It is as if you are in a more hot climate. So that's why you have to bump up the high temperature rating by 1 grade. So if you were at 64, you need to look at the table and go to the next one, which is 70. Let's look at the table. So if you were at 64, then you go to the next one, which is 70. And the same things happen if you have a slower speed. If the speed limit in the road that you are designing for is very low. If you expect to have very slow trucks. And if you have both, then you have to go up 2 grades. So this is something we didn't talk about, and this is something kind of you need to adjust the binder design. Questions about that? Clear? Great. Okay, we are done with this. Yes, please.
What about like for highways? If since you have fast traffic and a lot of volume, but then sometimes you have bumper-to-bumper traffic and you slow traffic and kind of volume.
You always are conservative. So you always try for like high volume highways, like, I don't know, New Jersey Turnpike. what I think about. And you are always going on the very conservative side to make sure nothing happens. They collect a lot of traffic data beforehand, so you have some ideas of how much slow traffic you have, what is the volume, and then you take everything into account, being conservative as a good engineer. Good question. Okay, now we are done with material selection, the binder. The next is aggregates. As I told you, you want to have angularity. So if you have round aggregates, of course it's much easier for them to slide, and you are going to have more rotting, less stability. So angularity gives us internal friction and resistance to rotting, and I hope the pictures show you why. So you need to have a minimum percentage of angular, fine, and coarse aggregates. So as you can see here, and angularity, I hope you remember from aggregates, that means when the aggregates have like fractured faces. They are not round like riverbed, what you would get from a riverbed, round pebbles. So that's one criteria. And then the next criteria, this is, okay, and there are some tables in the design code to make sure that you are choosing enough angular aggregates. So you see, depending on the traffic level, which is defined based on EZ, you have to have a minimum percentage of angular, fine, and coarse aggregate. At the same time, you don't want to have much flat and elongated aggregate. You remember why? Why don't we like flat and elongated aggregates? Easy to break. So they're terrible for during compaction of asphalt. They're going to break, exactly. And sand equivalency tests for the amount of organics and clay. You don't want to have too much of that, because then your material becomes susceptible to stripping and the binder doesn't glue to the aggregates very well if you have a lot of clay, etc. So the larger this is, the cleaner is the material. For coarse aggregates, angularity, we have talked about this before, means that you have a minimum percentage of particles with one or more fractured faces. For fine aggregates, you may remember that you need to drop them from a cone, and then you have a specific weight, you have a holder with a known volume, and you measure the weight. And from that, you have some idea about the angularity. It's not very accurate, but this seems to be working fine for HMA design. So this is what I just explained to you, written in words. How about gradation itself? So there is this gradation here, and I hope you still remember this 0.45 power graph. So here is size to the power of 0.45. And if you remember, the straight line is the perfect dense gradation. And you have some control points. You have some on the maximum size, and then some in the middle, and some at a low, like fine aggregate size. So your gradation it is like a motorcycle test. It needs to go between all these control points. So you need to have something very close to the high density. You need to have all a relatively continuous gradation curve to be able, for the material to be able to check for superpave. I think the graph is not drawn in your notes, so if you want to just draw it once to see how it feels. really think about it as a motorcycle test that you need to go. If you want to get a driver's license to do a motorbike, you need to, at least in Germany, I don't know here, you need to go through this. Okay. Yes.
Do you have a motorcycle license?
I have one in Germany. It doesn't. It's not valid here. That's a good question. Very relevant. It just reminds me of that because you need to you need to not hit certain obstacles. Do you have one here?
No, I like mountain biking.
Okay, that's different. Doesn't need a license either, as far as I know. That's what I do too without license. Okay. And this is kind of putting everything together. What type of material you want to have for super paved mix in terms of soundness, angularity, in terms of flat and elongated, and everything that we talked about. It's a summary of what you need to have to pass the test. So now looking at these two mixes, which one do you think is conforming to super paved mix? Right or left? Which one, right or left? Right or left? I think left is a better one. The right looks a little bit more like uniformly sized. And here you are going to have different sizes. The aggregates a lot of them are angular, those are two. But then you have a lot of different sizes, including fine aggregates. Here, most of the aggregates are pretty much in the same size range. So, just to get a sense. So we are done with these two, and now we go to the next step, which is the only one which you need to be really careful about and pay attention, especially because this was not included in any homework, and it needs a little bit of calculation. So the way we choose the binder is that you kind of estimate the binder content, and then you add plus minus to that binder content, and then you calculate VTM, VMA, and VFA, you measure these, and then that's how we design it. So what you learned in HMA, volumetric calculations, this is where you have to use it. So the way you prepare the samples is using this gyratory compactor, which is I've given you the numbers, but I think there is a better picture. Yeah, this is how it looks like. So it compacts while rotating the sample. It's a special equipment. You apply a pressure, and there is a certain angle, and the number of gyrations depends on the expected level of traffic, as you can see here. So if the easel, remember, if the number of equivalent single axle loads are low, medium, or heavy, you are going to have different gyration numbers. You want to kind of imitate the compaction that the material experiences during construction and service. So that's why it depends on the traffic. Every truck that passes over the material is going to compact it a little bit. So that's why this is like that. Now, we go through the design, as always, with an example. And this example is in Milwaukee, a highway, I-43, for example. We have the aggregate blend, the maximum size aggregate is 19 millimeters, and we already have the PG binder selection, 5834. So the steps are written here. So we first estimate binder content, then we have to calculate VTM, VMA, VFA, and then we check with the criteria. So please pay attention. It's just the best use of your time to pay attention right now to learn it. It's very, very simple, but you just have to listen to it once, and then you know. Simple. So how do we estimate? Just as in concrete, it turns out that there are tables to help you. So if you know the nominal maximum size aggregate, then you estimate. This is how you start. But everything in HMA pavement design is it's not very like hard science accurate. So you add plus 0.5, minus 0.5, plus 1, minus 1 binder, and you calculate everything for them to find the best binder content. You cannot just use this number you got here. So this is how it looks like. So you put your 4.5 that you got from the table here, and then you look at the ones which have minus 0.5, minus 1, plus 0.5, plus 1. So this is how you go. So GMB, which is the specific gravity, the bulk specific gravity of the mix, and the maximum values, last time I told you how we measure that. If you are working in PennDOT, let's say asphalt lab, you need to measure it. In the class, of course, I need to give this to you, these numbers. But remember last time I told you how we get those? You have to, for GMB, you have to use compacted samples, get the buoyant mass, SST, and dry mass. And for GMM, you have to crush it, and actually you have to work with the powder because you want to have all the air out. That's the only thing you can not have any air. Anyways, imagine that you have a lab and you could get these numbers. And now, this is the point where you need to use your knowledge from last time to calculate this VTM, VMA, VFA. These are these different air contents that you also, I guess, calculated for one of the problems you needed to do that. Correct, today? So, we don't go through those details again, but this is what you need to do to use the relationships or to use approach number 2, however it is. It's a good idea if you want to check these numbers and do this as practice at home. But I assume now that you did the homework, we are all fit to do that. And once you complete this table, then you can actually start with the design process. I can upload the completed notes, so don't worry if you don't have it because there are some graphs. So, the way it works is you first start to plot these two rows. If you are writing, it's fine. You can also write it. You plot VTM versus PB. You see how by changing binder content, the total air work is changing. It will look something like that. If this question appeared in the exam, which may, you need to use Excel or you need to plot this. It can happen. Okay? So it's nothing more than plotting. So look back here. This is column number 1. And then this is number 4, 5, 6. So all you do is, this is number 1. You're all engineers. You plot VTM versus binder content. And why do we do that? Because SuperPave tells us that the best binder content that you may have is that corresponding to a VTM equal to 4%. So whenever you see a SuperPave mix design, VTM, you know beforehand is 4%. Why? This is experimental. I cannot tell you. They just have found out that they perform the best. In pavement design, a lot of things are experimental, based on experimental research. It's not, I cannot give you an equation why. So how does it work? You take the 4%, go to your curve, and then you get the binder content. And then you need to check if this is okay with 2 other criteria. So remember, the first step is to plot VTM versus PB, 4%, always 4%, always. Go and see what is binder content. If you see a problem in the exam which says this is a SuperPave mix, immediately think VTM is 4%. That's the only thing you need to remember about SuperPave mix. VTM is 4%. This is what it is. Okay. And once you get that, then we need to check a few things. This is what VTM is. We need to check VMA. We don't look at everything here because that will be its own course, and there is a graduate course on pavement. But we need to check to see if VMA is good. So you take your you take the binder content that you got from the step before. You go to VMA versus PB. This is column number 5. Plotted versus column number 1 from the table. And you go and read the VMA. And then you go and check. So this is how it looks like. So you go from 4.7 here and go and read here, which is like, I don't know, 25 or something like that. So the other one, we started from 4 and went to here. Here you start from 4.7, which you got there. Okay? You go to this table. The nominal maximum size was 19. You have to check that the number you get is greater than 13. Which is? I got like 13.25. Is this clear? What's going on? So you start with VTM 4%, you get the PB, you get the PB, go check the VMA. And now we also have to check VFA. And then we are done. So after you check this, there is another one, and that's VFA. And this one, you need to look at the number of easels that you have. What is the design easel in millions in this problem? How much was it? I don't hear. 15? 18? Okay, so it is here. You need to have a VFA which falls between 65 and 75. And as you guess, you are plotting VFA versus PB also. You have these three plots. You go and check 4.7 and check whether you are between 65 and 75. If you are not, you need to change your gradation typically. So if there is a question on this, it's more to check. I don't expect you to really design with the information that you have. It's complicated. So let's sum up what we did. 4% VTA, then you get the binder content, and then you go to use that binder content, you check that VMA and VFA are within the ranges that are given by SuperPave. Very simple. It's not hard, really. Okay. These are some, just wanted to remind you what each parameter is. So, we are done with step number 3. The only thing to check is moisture sensitivity. And the way it is done is you use the samples that you have with the design, gradation, and binder content, and then you subject them to a population of them to freeze-thaw and saturation. And afterwards, you measure the tensile strength and you look to see how much it has lost tensile strength. And it should not lose more than 80%. And then you are okay. So you want to see how susceptible is your mix to moisture. So you subject it to accelerated severe saturation and freeze-thaw cycles, and then you measure to see how much tensile strength it has lost. Simple. There are more details, as I told you, but really it's beyond this class. If you know these 4 steps and you understand what we talked about today, you know enough at this point, if you don't want to become a pavement engineer later. Now, a few words after you design this. Of course, you need to produce. Now you got your design right, everything is good. Now you need to make this happen. You need to produce and construct a pavement. In the old times, people were using this kind of batch plants where the aggregates were heated separately and then binder was heated and things get mixed. Now, oh, there is a nice picture here. So it's like showering the aggregates. But the one which are being used right now are these drum plants. So you have a double. Oh, what happened? My stylus doesn't write from time to time. Double barrel drum, and aggregates are heated in the inner drum and they are mixed with the binder in the outer drum. And as you can see, there is a lot of heat involved. Has anyone seen asphalt production? No? After you do that, of course, you need to load them on trucks to bring them to the site. One thing is very important, and that is that you want to make sure that the material doesn't cool a lot. So typically you have to cover it, and nowadays I think it's common practice now to use infrared cameras to make sure that the temperature is uniform and you haven't lost much. So you just shoot a camera and you see the temperature distribution. Has anyone seen an infrared camera? No? It's like, you have maybe seen it in movies. If you want to find someone in a jungle, because the person is hotter than the environment, so you may have seen something which shows a color of difference if an animal or a person is running in the bushes because of the temperature change. There are higher sensitivity ones which are now being used in construction. And then, of course, you need to place the material, and you use something which is called paver. Everything is now very automatic. You want to make sure that you don't place things in too thick layers because you need to compact each layer nicely. And normally, you want to have each layer about 2 times the maximum size aggregates. And then you place one layer, you compact it nicely, you place another one. Compaction is super important. It ensures that you have the sufficient porosity, or you have not too much or too little porosity in asphalt, which controls everything. So compaction during placement is very important. If you have areas which are very hard to reach, you have to use manual placement. You cannot use the big paver. Next time you see an operation, pay attention to these. And then you need to compact it. Of course, as I said, it's essential for good performance. And you may have seen these rollers, hopefully, at some point when you were driving and there was a road construction. And they do the compaction for you. And basically, after compaction, you are done. So